The next section is 7.3, ratios, variation, and proportions. Let's look at one that's in the book. I kind of like this one. Suppose you're buying, I forgot what he said it was, say peanut butter, and you've got three options. You've got $3.49 for an 18-ounce jar, or $4.99 for a 28-ounce jar, or $6.79 for a 40-ounce jar. Okay, and you want to know basically which one is your best price. Typically in the grocery stores I go to, they actually have a little sticker down below that gives you the price per ounce, and that's what we're going to calculate here. So the price per ounce, this is your price, and this is per ounce. Per means divided by. So if you basically take $3.49 and divide that by 18, you end up with, brought my little calculator along, 3.49, enter, 18 divide, and you get 62 point, let me do that again, 3.49, 18 divide, get 0.1939. That's going to be dollars per ounce, so about 19 cents an ounce. On the other hand, if you go $4.99 divided by 28 ounces, you get what? $17.8 per ounce. And the last one, if you go 6.79 divided by 40 ounces, you get $16.98. I should say 0.61698. There you go. So that's the idea. Okay, simple enough. You've probably seen those kinds of things before, but anyway, that's ratios. Okay, the ratio here is the smallest ratio, and of course that's the largest. So this is your best buy per ounce. Okay, that's very good. Here's another one. This is an example from my experience when I was in high school. My father was reading a article about the population of the world in Reader's Digest, and I was sitting across the room, and he asked me this question. He said, so this is around 1975, somewhere in there, I guess. And he said, how many cities are there in the world which are over 1 million? How many cities in the world are over 1 million? And here's what I did. I'm kind of proud of this, okay? I had just read recently that Houston, Texas was the 10th largest city in the U.S., and it had a population of just over 1 million. Something like that. I can't remember. It was just barely over 1 million. So here's what I did. And I also knew this. I knew that the U.S. roughly had a population of 300 million. And I knew that the world population was, at that time, roughly about 6 billion. Okay? So that's what I knew. I knew that. And the question is, with that information, what kind of guess could I give them? And here's what I did. I said, well, I knew this. I knew that the 10th largest city was just over 1 million, and so likely the 11th largest city was less than 1 million. So my guess is that there were 10 cities in the U.S. that were over 1 million. Okay, that was just my guess, knowing this. And then I looked at this and I said, well, what's the ratio of the U.S. to the world? If you take 300 million and multiply it by 20, you're going to get 6 billion. So this is 20 times as big. That's 20 times, basically the U.S. has 1/20th of the population of the world. Okay, it did back then, and it does still today. So I just set up a proportion again. I said, well, basically, since there's 10 cities in the U.S. with 300 million, how many cities would there be if there's 6 billion? And I just thought, well, since this is 20 times as big as this will likely be around 20 times as big as this. In other words, roughly 200. Now, I was making all sorts of assumptions then. I was assuming that the world's population was distributed somewhat kind of similar to the U.S. population, but I didn't know otherwise. And so that was my best guess. And so I said 200. And I still remember my dad just looking at me wide-eyed, and he says, "Have you seen this quiz before?" I said, "No." And he said, "You got it right on the button." So anyway, kind of a fun use of proportions there. Okay, so there's that. Okay, so let's talk about this kind of thing in a little more detail. The kind of thing we're talking about is called a direct variation. And it's easiest to see a direct variation in a table form. Say this is your x and this is your y. And those are the values of x. And these are the corresponding y values. Say the corresponding y value here is 5, 10, 15, 20, 25. That's a direct variation. These are directly proportional to this. One way of writing it is to say that y is proportional to x. That's a little proportionality thing there. It looks like alpha. Kind of looks like that. I sometimes tell my students that there are a lot of mathematically inclined people in West Michigan because you see a lot of cars with bumper stickers with that little alpha on the back of it. So anyway, kind of cool how many alphas you see around. But anyway, so there it is. I guess it could be a fish as well. But anyway, that's one way to write it. The other way to express it is to say that y is equal to some constant times x. They're both saying the same thing. These are 5 times as big as this, so you can just say they're proportional, or you can actually put in the value 5 and say you get y by going 5 times x, and that gives you the y value. So those two things are saying the same thing. Okay, so as an example, suppose you go, maybe you're hiking on a rather fast hike, and you go 15 miles in 3 hours. Okay, and the question is, how far in 7 hours? Okay, so how would we figure that out? Well, distance is equal to rate times time. We talked about that already, so there's a nice proportionality, and we can figure out the rate from this. What is the rate? You went 15 miles in 3 hours, so d divided by t is equal to r. In particular, 15 divided by 3 gives you 5 miles an hour. See that? There's your rate. So now that you have your rate, if y is your distance, and if let's just let x be equal to your time, then we see that the distance is equal to, in this case, 5 times the amount of time. So there's your relationship. And so now that you've got this 5 discovered, you can use it for anything. So how far in 7 hours? Well, in 7 hours, you go what? 5 miles an hour times 7 hours would be 35 miles. See, so there's a simple example of a proportion. Okay, so I'll give you kind of one quick example of a bunch of these, and you learn this stuff like you learn most stuff by seeing several examples, and so your teacher in class will have more time to do more of them as well. Here's another one. If there's no air friction, the distance that something falls is proportional to the square of the time. Okay? It's proportional to the square of the time. Usually t is in seconds and d is in feet. It doesn't have to be, but a lot of examples, that's what we'll use. That's what we're going to use this time. So that's the case, okay? If you want to know how far something falls, this is the case, which means that you can write d is equal to k times t squared. So this is not proportional to t in this case. It's not a direct variation. Instead, it's proportional to t squared, okay? So this is a proportionality, distance is proportional to the square of the time. And so here's my first question. Question 1. If it falls 3 times as long in time, how much farther? Okay? So the time is 3 times as long. How much farther will it go? Okay? Well, let's think about it. Suppose that let's let d1 be how far it goes if it falls t1 seconds. Okay, we often use little subscripts like this to help us kind of distinguish things. And so now, if t2 is equal to 3 times t1, okay, if it falls 3 times as long in time, then what will the distance be? Well, then d2 is going to be that same k, whatever k is going to be k times d2, the same relationship, but we know that d2 is 3 times t1. t2 is 3 times t1, so this is going to be k times 3 times t1, quantity squared. And now you can square this out. You're going to get k. 3 squared is 9. t1 squared is that. And notice that we have 9 times the quantity k t1 squared. Okay, which is 9 times k times t1 squared. That's d1. d1. So in other words, if it goes 3 times as long, it's going to go 9 times as far. See that? If it goes 3 times as long, it's going to go 9 times as far. And kind of the key to this is notice that we never had to actually find what k was. Okay, we just used the relationship that this was 3 times as much as this, and so we got 9 times the distance. Okay. So if this was directly proportional, then if you had 3 times the amount of time, it would also be 3 times the amount of distance. See that? But this is proportional to the square of the time. So now if you go 3 times as much time, you don't go 3 times the distance, you go 9 times the distance. That's the key. That's the key. Okay, let's do another one. Let's say that this is number 2 here. Suppose that you go 400 feet in 5 seconds. And the question is, how far in 10 seconds? Okay, if you go 400 feet in not in 5 seconds, how far in 10 seconds? Well, given this information, we can actually find k. So I can actually go, well, here, what do we have here? We have 400 feet is equal to k times 5 seconds. 5 seconds squared is going to be like that, which is equal to, what's 5 squared? 5 squared is 25, 25k. And now I can divide both sides by 25, and I get k equals, I know that 4 quarters give me $1, so 16 quarters will give me $4, so that must be 16. So there I actually found the value of k. The advantage of that, it takes a little work to find the value of k, but once you have it, now you can solve lots of different things with it. So here, let's just write, here's our equation again. D is equal to, here's our value of k, 16 t squared. And so after 10 seconds, what's it going to be? It's going to be 16 times 10. Quantity squared is 100 times 16 is 1600. So 1600 feet. This is all assuming no air friction. Okay, friction slows things down, but assuming it's really heavy or very light air, then this would be the case. So there's the answer. We got this answer by actually solving it for k. Notice that this particular one as well, we could have just noticed, oh, 10 is twice as big as 5. So if this is twice as big as this, you're going to have a t which is twice as big. So what do you do with that twice as big? You square it. So it's twice. So 2 squared is 4. So it's going to be 4 times as big as this. Sure enough, that's 4 times as big because the time was twice as big. Okay? So we could have done that either way. Okay, let's try another one. These are very important problems. The nursing department at Davenport was especially interested in us making sure that you knew this stuff well, because nurses have to do things like, well, if a person who's 100 pounds gets this much medicine, how much should a person who's 180 pounds get? And you might have to do things by weight and so on. So there's lots of use for this. Here's a relationship. Pressure is proportional to 1 over the volume. This is if you have a set amount of gas in a container. So if you've got a balloon or something like that, or you've got a cylinder, and as you push on the volume and make the volume less, the pressure is going to increase. So you can either write it like this, or again, you can write it like this. K times 1 over P. If it's K times 1 over P, you can write it as K over P. Okay, the proportionality constant is always best put up on the top like that. Okay, so there's a relationship. And so given that relationship, let's just answer this question. If the volume doubles, what happens to the pressure? Okay, if the volume doubles, what happens to the pressure? Well, let's do this one as before. Oops, I should have had a P there. Okay, so I could have started off by saying here's the original situation. If the volume is V1, then the pressure is P1. And now we're going to do what? Now we're going to double the volume. So V2 is going to be twice as much as V1. See that? It's going to be twice as much. So what will P2 be? P2 is going to be K over V2. Okay, that relationship always holds. But now V2 is equal to 2V1. And notice that that's equal to 1/2 times K over V1. And K over V1, that's just P1. 1/2 P1. So in other words, as you suspect, if you double the volume, this is going to make this twice as big down there. And so now the pressure is going to be half as much. That's why we call that an inverse relationship. Because now as one gets bigger, the other one gets smaller. See that? The other ones, as one got bigger, the other one got bigger. Now as one gets bigger, the other gets smaller. Let me just make sure that my computer's still working. Yep, it is. Okay, very good. Let's try one more. Okay, there are a lot of problems like this. You've got a course enrichment project, a CEP, that has a lot of good problems like this that you're going to be working on. Here's another relationship. The weight, a person's weight, is proportional to 1 over d squared, where d is the distance to the center of the object. Okay, so believe it or not, as you, well, maybe it's not hard to believe, as you move away from the center of the earth, your weight is going to decrease. You're going to weigh a little bit less on the top of a mountain than you would if you're just by the sea. Okay, and the distance that you're always interested in is how far away you are from the center of the earth. That's why when you go out in space, obviously, it's going to become even less because you're farther and farther away. So here's two questions I have. If 3 times the distance how will the weight change? Okay, let's do it. So let's first say that weight is equal to K over d squared. There's our relationship using a K rather than the proportionality constant. Then we'll say, okay, in the original configuration you have a certain distance and you also have a certain weight. So that's true. And now, what do we have? We're going to have 3 times the distance. So now your d2 is going to be 3 times d1. Okay, it's going to be 3 times d1. So the question is, w2 is equal to k over d2 quantity squared. It's true no matter what the distance and weight are, they always are related like this. But now we know that d2 is 3 times d1, so what do we have here? We're going to have k over d2 is 3d1 quantity squared. If I square this out, you have to square everything inside, so 3 squared is 9. And here you have d1 squared. So that's going to be 1/9 of k over d1 squared, which is equal to 1/9 of w1. Okay, so what's happening here? Since it's proportional to 1 over the square of the distance, if you make the distance 3 times as big, it's not just 1/3 the weight, it's 1/9 the weight. Okay, so it's first of all it's the reciprocal and also it's the square. Okay, and let's do one other one. If W is equal to 100 when the distance is 5, what is W when distance equals 6. Okay? So let's first use this. First of all, notice that there's not a nice, easy relationship between 5 and 6. We could find it, but I think it's easier just to go ahead and find out what this k is. Let's go ahead and do it. So this is our relationship, and so let's find out what k is. So if w is equal to 100, and here you have k over, and 5 squared is going to be 25. See that? K over 25. Now you can solve it for k by multiplying by 25, and you get k is equal to 2500. See that? So there's 2500. There's your value of k. Now that you have that, you can easily find anything you want. It's kind of nice to solve for your constant if you had a bunch of them, especially if you said, what's the weight when you're 7, 6, 7, 8, 9, 10, and you have a whole bunch of them. Then you might as well solve for k. And now we're going to get 2500 divided by 6 squared. And I'll go ahead and calculate that as long as I have a calculator handy. 2500, 36 divide, 69.44. Okay, is what you get. So very good. So that's variation, and that is section 7.3. And as I say, you've got some nice, interesting CEPs to work with in this section.